Our title for today is Wheat Evapotranspiration and the Crop Coefficient under Different Production System for Improving Water Productivity in Urban Region. I'm Rania Gamal. I'm a researcher inside Water Agronomy team in Parta Cairo. First, I would like to start with the problem we are facing in Egypt. We are facing the climate change phenomena. As all of the NENA region, we have also limited water resources. Egypt receives a fixed amount of water, which is 55.5 billion cubic meters per year, according to the agreement of Near Water Agreement 1959. We also facing water scarce, and we are expecting to cross extreme water scarcity by 2025. The country experience fast population. Unfortunately, we are increasing like 1 billion every 6 months, which is a very big number. We have also high cost of energy in agricultural operations that affect the grower net profit. We have a big gap between production and the consumption. As we see in the next graph, we can see the production is slightly increased, but the needs and our consumption is increasing very fast, as you see in red line. And we can see also the big gap, it's increasing day after day. So we have to close that gap or even to make it decrease. We have also lack of actual evapotranspiration measurement in Egypt due to the high expenses of agrometeorological stations. It's not easy to buy it, and it's also require an special knowledge to monitor it and obtain the data. We have evapotranspiration based remote sensing model, and it also need to validate and calibrate its data against actual data. And most of the simulation models built in different region, and we have to calibrate it to be suitable for our NENA region. So Egypt is one of the NENA countries that we have to strategically analyze and plan our water resources. We have to assess our surface and groundwater resources depletion and recharge rate. We have to implement an effective solution for determining the best utilization of each drop of water for different cropping system under different soil crop management practices and climate conditions. So as the objectives of this study, I have three main objectives. The first one is to quantify and analyze the absolute water saving, which is water, we can say actually evapotranspiration also, under raised bed and under flat bed. For the new high-yielding bread wheat cultivar, it's called Masr Wahed. So the main object is to study the ETA under raised bed and traditional practice, which is flat bed, for investigating the feasibility of both production system in Egypt. The second is quantify and determine the amount of water saving in irrigation schedule. If we did irrigation schedule based on our actual evapotranspiration, and if we did it according to FAO 56, so we can say the traditional method. The third, to identify and quantify actual evapotranspiration using integrated satellite data for sustainable water management in Egypt. Material and method, we have two locations. The first location located in the middle of Egypt, sits station in the middle of Egypt, and it has extreme weather condition. We have a very high temperature there. This is the first place. We have 8 fadan, and we can say it's 8 acre. The second location is Sakha Station, which is one of the NENA region location in Egypt. And the size of experiment there is about 10 acre. We installed the energy balance flux tower in both stations, as you see in the figure. The experimental design and the treatment, all the treatment or the agronomic practice were the same in both stations, except the cultivation method. We have in Sista station, which suffered from the high temperature, we have a raised bed, and in Sakha station, we have a flat bed. Both we cultivated on 25 of November, and we were installed calibrated energy balance in both experimental sites. We have several agronomic practices. We can say land preparation, we can say desert leveling. They are, as I mentioned, the same in both stations. We have here the raised bed. We installed here in this picture weather agronomic practice, weather agronomic station, and here is the raised bed in the beginning of the season. It's and here is after a while during the growth stage. The installation of energy balance in Sakha station, we can say here is the steps of the installation in Sakha station. And also we have installation of energy balance flux tower in Sakha station, which require a very high effort. We can say dating to install it, and it requires installation till like the night from the beginning of the day. So it's very hard work to install it, to install the station. After that, we can say the zero behind this is the energy balance flux tower zero and energy balance equation. Most of all already know. I want to shed some light on this. It's taking into consideration the soil heat fluxes, and it takes into consideration the heat capacity of soil, moist soil, bulk density of water, heat capacity of dry mineral, soil water content on a mass basis, soil water content on a volumetric basis. So if I wanted to compare both stations, yeah, it requires and taking into consideration the soil characteristics and the soil difference because of the sensor which we are installing in the soil. Many models that we can obtain EG from, we have a metric, we have vapor, we have CBAL, and of course we have to validate and calibrate this model according to our actual evapotranspiration. So the third objective was to build a remote sensing suitable for our NENA region, suitable for Egypt. And this model based on two parts, thermal condition factor and vegetation condition fraction. Thermal condition factor, it depends on land surface temperature, and we can say that land surface temperature is high in the desert or van soil, and we can have lower land surface temperature in water streams and cultivated area. At the same time, the second portion, which is the vegetation condition fraction, depends on vegetative condition and vegetation density, physiological stage. It's our crop suffering, or it's healthy, or stressed. The result we can summarize it as we have obtained before, and the finding is already in a good agreement with what have been found and stated before in ICARDA. That raised bed already increased the grain yield by 33%, as we can see. Also, we applied a less water in raised bed rather than in flat bed. For crop water productivity, if it based in applied water, it increases 55% in set station, which was flat, which was raised bed. So the raised bed increased the water productivity. As we see here, if it based on applied water, and if it based on ET, the both water productivity is already increased. I wanted to shed the light on which stage during the production of wheat can consume the biggest amount of water. So, according to our result, actual result, we can see in the physiological stage it consumes the most amount of water in both stations. It's not. For the reference evapotranspiration, the accumulated ET node in Sakha station was 433, and the accumulated ET node in Sakha station was 557. which reflect the fact of the increasing temperature of the station on the ET. Of course, the ET node in a higher temperature, we can get a higher value of ET node. For the energy balance component, as we can see, the highest component is net radiation following by latent heat. After that, and I consider that the most important figure in this finding, we can see, however, the high temperature in the station, the effect of Risdebit here is very clear. It reduces the effect of evap ET, like it reaches the same numbers, the same value of Sakha station, which not suffering from the high temperature from the beginning of the season till mid of March, which is the starting from the summer season, and then it varies with an increasing about, as a total increasing is 15%. However, the increasing in ET, or the difference in ET, was 32%. So we can see the contribution of Risdebit. It reduced the amount of actual evapotranspiration by 15% in this study. The second objectives, we can see the comparison between energy balance station measurement and Bellman-Multis method. If we want to do like an irrigation scheduling, if we want to depend on FAL 56, and if we want to depend on our actual evapotranspiration in the irrigation scheduling. We can see that the dotted line is the ETC from FAL 56, and it has we can say overestimation more than the actual evapotranspiration. And here is also, it's very clear that the difference between ETC from FAO and the accumulated ETA from energy balance, the difference is about 762.8 cubic meter per fadden or per acre, which is already a big number. The same comparison have been made for the second site, which is Sakha station, and we got the same result. What is amazing of this graph and the trend, thanks to Dr. Allen for FAO 56, we have the same trend. We have a peak here and we have here. Yes, it has an overestimation, but look at the trend. It's up and down with the same pattern. This is really amazing. However, as we said that the ET depends on the FAO 56, it has a higher value. And here the difference between them was about 555 cubic meter per fadden. So we can summarize and emphasize that using modern technologies like energy balance can give us an adequate amount of irrigated water, can save more water for best irrigation scheduling for wheat in Egypt, if it's in Delta or in Middle Egypt. The last objective is quantifying the evapotranspiration using our new model, which have been already described. The dotted line, which is the data obtained from the new model. And we have here the only difference between actual evapotranspiration with energy balance and actual evapotranspiration. It depends on remote sensing. The new model we already have built. I have to mention that this data have been published successfully in agronomy and 2 or 3 months ago. Here we can say, return back to the result, the difference is only 43 millimeter per season in cyst station, which is seems the model is reliable and we can depend on it in our calculation. The same steps have been done for Sakha station. The only difference here was amazing. It's only 7.2 millimeter per season at Zaha station. This is the difference between the energy balance and the new model. And finally, thank you so much.
Thank you, Rania. So now it's the time of last presentation.